So the purpose of Runge Kutta is to get a more accurate projection using a differential equation of where your line is going to be going. So it's similar to Euler's method, but in Euler's method it's a lot simpler. As you can see, this is Runge Kutta, this is Euler's. Euler's method just use your initial point, and then you're trying to get to this point, so you add the slope times the change in x. These two would cancel, and it would give you your new point. But using Runge Kutta, they came up with a much more complicated version, but it works better because it's more accurate. So this one still has where you want your next point over. This is your initial point, and then this is the equation they came up with, and all this stuff just finds the slope, and then you're going to multiply it times the height, which is the same as how we multiplied it times delta x before. So you're going to multiply it times the height, and then that's going to give you your new point, and then using a computer or something, you could generate it over and over again and get a lot more accurate as you go on in time. And then for these values in here, they came up with all these different values, and each one you're gonna, for this one you just use your initial points, and then you're gonna plug it into whatever differential equation you're given. And then for this one, you're gonna plug it into your differential equation, but also multiplying it by k1. And then this one uses k2 to find k3. This one uses k3 to find k4, so they kind of build off each other, and that's how it can be really accurate.
Okay, so using the equations we just discovered or came up with, we're going to show an example of the Runge Kutta method of solving our initial equation of x squared, dy dx equals x squared plus 3y, with our initial condition of y0 equals 5. So we know that our f of xi or y of I equals, since I is 0, our x of I is 0 and our y of I is 5, because it gave us our initial there. So we'll use k1. K1 equals f of xi, yi, and we know what those are, so it's 0, 5. Then we have to plug those into our original equation. So we'll have 0 squared plus 3 times 5 equals 15. So k1 equals 15. Now we have to go down to our k2 value, k2 equation, I'm sorry, for the Runge Kutta method, and we find that k2 is f of xi plus h over 2, and we have an h, which is our step size, of 1. And then our y plus h of 2, h over 2, and times our k1 value. So that becomes 0 plus 1 over 2, comma, our y, which is 5, plus 1 over 2 times 15. So k2 I'm sorry. Where am I? I lost my place. Oh, there we go. So our k2 becomes f of 0.5 and 12.5. So we plug that back into our original equation again to find our value of k2, because we have the point of k2. And that becomes 0.5 squared plus 3 times 12.5 equals K2, which equals 37.75. So now we're not done yet. Now we have to go to K3. So K3 is f of xi plus h over 2. It's much like K2. So yi plus h over 2. This time it's times K2 instead of K1 like we had originally there. So we plug all these in. We will have our xi was 0 plus 1 over 2, comma, y initial was 5 plus our step size over 2 times our K2 value. So that goes right into there, and that is 37.75. Now we end up getting the point 0.5 and 23.875. So then, plugging back into our original equation again, we get 0.5 squared plus 3 times our value here, 23.875, equals our K3 value, which turns out to be 71.875. Now, finally, we have the Runge Kutta method, K4 now. So, and that's why this is done mainly in computer programs, because it takes a long time to get our next step, but it's, very accurate depending on your step size. So our K4 is a little bit different. It is xi, or x initial, plus our step size, and then our y initial plus h times K3 value. So that turns out to be 0 plus 1 and 5 plus 1 times our K3. Which is, oops, marker foul. Okay. So we get the point 176.875, and then when we plug that into our equation once more, we get 1 squared plus 3 times our 76.875, which equals our K4 value, which is 231.625. I can drop out. There we go. Okay. Now I'll come over here. You can see over here. Mm-hmm. Okay. And we have to use this equation that we came up with earlier to find our next y value when we step over 1. So y1 equals, and we use our y initial, which was 5, and then plus h, which was our step size of 1 over 6, and all that times our K1 value, which was 15, plus 2 times our K2 value, which was 37.75, plus 2 times our K3 value, which was 71.875, plus K4 value, which was 231.625. And we find that our y1 value turns out to be 82.6, which is our next y value using a step size of 1 from our original differential equation. Okay, graphical representation of what just happened using the Runge Kutta method. So take, it's our x, it's our y, and we remembered that our initial value of x was 0, and our initial value of y was 5. So we had a point right there, that's our initial. Then, because we knew our step size, h, is equal to 1, so that's basically like our change in x. So our next area would be right here, which would be 1. So this is our step size. And we found that to be 82.6. It was our next y value. So because we use such a big step size, we don't technically know the shape of the graph. So we're just going to represent it as a straight line. Later on we will use computer methods to figure out the exact slope and the exact shape of the graph. But so we have a change right here, which this is h, and then right up to our point, which is, this is basically our y0 value, and this is our y1 value that we found using the method. So the smaller the step sizes, the more accurate this curve will be, and the more accurate this number will be to the actual value.
Okay, we took our differential equation, solved it, and punched it into the graphing calculator and came up with this table that shows us when x equals 1, y is equal to 101.95. Okay, we've also been told that that the Euler's method, or Runge Kutta, is the new and improved Euler's method. And if we go over here to Excel and we punch in our differential equation of x squared plus 3y with the initial conditions of when x is 0, y equals 5, we can see that with the step size of 1, with the Euler's method, that when x is 1, y equals 20. And 20 is quite a ways off from the 101 that we saw on the graphing calculator. So with the new and improved Euler's, which is Runge Kutta, here in our fourth order Runge Kutta, we can see that when x is 1, that y is 82.64583, which is considerably closer and more accurate than the 20 of the Euler's method. And so by that we can see here how much Runge Kutta is improved over Euler's.